maybe I'll make a brief introduction, if you don't mind.
Yes.
So this is the abstraction seminar. It's got ambitious goals to understand three hard things and how they relate. I think we'll save the sort of general picture for next time or later, since it takes some time in and of itself to explain what we have in mind. And I think we'll just get straight into it with Alexander speaking on natural abstraction. Thanks, Alexander.
Thank you, Dan. So yeah, I'm Alexander. Those that don't know me, well, I should maybe give a little more introduction. I work in AI alignment, and yeah, so I'm interested in understanding agency. And part of that is understanding abstraction, and I'll try and say a little bit about what uh, what that means, and hopefully that will give some um, pointers to why natural abstraction is so important, so interesting, and how it shows up in the real world. Or, yeah. So um, so the uh, uh, yeah, what we want is understanding agency in the world, in the real world. Um, and
Sorry, Alex, I'm standing in front of the board.
right, so biologists would say the bacteria wants sugar. It's looking for sugar that stays alive. And it's a very natural and very powerful way to think about bacteria. And but it's a very simplified description of an incredibly complicated organism, right? The organism has an enormous amount of variables. It is not. It has these extremely um, sophisticated machinery. Yet we think we can understand a very large part. We abstract in some sense, and we're able to say useful things. Now that's in some sense already a surprise, right? Why is this complex system? Why can it be usefully described in with such a short description? So that kind of leads us into agency. So much more broadly, we use agency to talk productively all the time, really, when we talk about plants, animals, humans, but also financial markets, political systems, neural networks, etc. Again, E. coli is an incredibly complex system. It has about 10 to 15,000 genes, and maybe you've seen these videos of these really incredibly complicated molecular machinery. It's not a homogeneous system, right? It's not like a system at thermal equilibrium. It is an incredibly non-trivial system. So how can we say anything about the system at all? We abstract the complex system as being made out of agency or having agentic parts. Right. Okay, so how do I on? Okay. So, right. So I just emphasize the point again. Understanding certain complex systems like humans, animals, financial markets through agency calc is a form of lossy compression abstraction, right? We kind of have this really complicated, complex system, right? But we compress it to, well, it is like an agent that is trying to towards a goal, and that agent is like the kind of actions it can take, how capable it is at taking these actions, and um, and the kind of goal that it wants to do. And that description is far shorter, so that far simpler. Of course, it doesn't. It's a lossy compression, but it's a very good lossy abstract compression. So that's one sort of intuitive idea of what abstraction means, lossy compression, in particular in agency. Now there's a blackboard. How does that work? Is that what does that mean?
Yeah, this slide didn't make it. I can.
I see. Okay. No, it's fine. Right. So once we identify complex system C as an agent, we can understand its behavior in terms of how well it reaches goals. So we use agency talk all the time. It's very powerful. However, most of that understanding is informal and therefore highly limited. So what we want is a theory of agency in real world systems. Okay, so we just, is it right there? Yes, okay. Let me see if the word canvas could, okay. And yeah, we want a theory of agency, but also of inferring agency. And I'll say more about that. And this is really about abstraction. So let me first talk about a very simple theory of agency or model of agency. So the question is, what is the type signature of agency, right? Well, very simply stated is an agent takes in observations and outputs actions, which maximize its utility function. Yeah, so it's maybe something like a strategy in a Markov decision process. And maybe it's a partially observable Markov decision process. That's a very powerful and simplified notion of agency. So there are a number of ways in which this picture is inadequate. So first of all, it assumes that the agent is a utility maximizer. That works for some agents, but certainly not all. And it assumes the agent, and I'll say more about that, it assumes the agent is separated from the environment. So it has like a boundary, Cartesian boundary. But real agents are embedded in their environment. But really, most importantly, it is silent on how to detect agents in the first place. How do I, if I have a complex system, how do I know that there is an agent in there? Or where is that agent even? How do I detect it? Where are there? How many are there? Are they maybe built out of pieces? And all these issues are related. So I'll sort of touch upon them, and hopefully that will be of interest. Okay, so let me say a little bit why we thinking of agents as utility maximizers is kind of too limited. Well, first of all, humans are probably don't seem to be quite utility maximizers. Or yeah, maybe we don't really know, but some often people object to that characterization. So we also like to understand agents as hierarchically structured out of subagents. So that makes sense for the markets or societies, but also for brains and neural networks. There's quite a lot of evidence that the brain is sort of hierarchically composed of sub-modules that have that also have some form of agency.
Can I ask on this point, wasn't the whole idea of formulating the idea of an agent is that it's too complicated to understand all the details? Why put them back in by thinking about it as made up of subagents and subagents of subagents and so on? What's the aren't you undoing somehow the abstraction that you were trying to achieve?
Well, the world, what is the Einstein quote? You have to describe it simply, but not too simply. Yeah, I mean, there are abstractions. Like when we have let's say a gas, right, a thermodynamic system. In a sense, there's like an optimal the Gibbs distribution gives it sort of perfect abstraction. However, a cell is not a terminal equilibrium. A brain is not a terminal equilibrium. So these abstractions are more complicated, and they will be hierarchically structured. They'll have interactions. It's more. That makes sort of sense.
Yeah, sure. I guess, like in the example of the bacteria before, I guess it truly is striking that there are sort of simple stories that you can use to reason about bacteria. I mean, then you can make the simple objection that, oh, that's too simple. You know, a bacteria is really made up of 12 billion agents of this and that kind interacting in this complicated way.
Right. So, and a bacteria is very simple. So it probably isn't that hierarchically structured in terms of agents. I mean, I really mean more complicated systems like brains and markets. These can be usefully thought of as being composed of hierarchically structured agents. But a bacteria, well, maybe you can do that too, but that seems to be, it's not like everything is an agent or something. Right. I'll try to go on. So one example, it is well known fact that markets are not utility maximizers. So economists call this no representing agent. And essentially, so they would say, oh, it's not an agent, but we still want to think of it as some sort of agent, of possessing some sort of agency. So essentially the problem is path dependence of wealth, of the individual traders that make up the market. So you can think of societies as being these alliances, and it can kind of start to depend on the specific path that you go down on how it ends up. And describing that with utility functions is not quite the right thing. So generally, combining utility maximizers may not give you utility maximizer. So this gets into voting theory of distributed systems. It's quite an interesting topic. What else did I want to say about that? What else? Let me. I wanted to say something. I think should be enough for now. Well, this is disappointing. All right, let me see if I can paint.
This was the Markov boundary and blanket picture, yeah.
Yeah, all right, okay. Cartesian boundaries. Yeah, okay, so our model is something like a large Bayesian network. So it has these nodes. I just gonna take a while to paint this. This looks like this. So I don't know. So at each node, just to remind you, you should imagine a variable, a random variable. And there's a joint distribution on all of them, and there's a distinguished factorization, such that our intuitive notion of, well, if there's an arrow from A to B, then sort of A influences is like is causally upstream from B.
Sorry, Alexander, you have to take a step back from the board again. Thank you. Yep.
Does this sound good though?
Yep. Mm-hmm.
All right. So okay, we do what we can. Right. So so this gets in the theory of causality. Pearl's theory of causality is incredibly important. It's still, I don't know. It's like me. Like, it's kind of the, if you don't know probability theory and now you do, that's kind of the I think the importance of this theory. So I can't say too much about that, but that's that kind of gets into this. So okay, I'm going to talk about a Markov blanket. So I can select a collection of states or of variables. So here I've sort of circled them with blue. And then a Markov blanket is a collection of its parents, its children, and the parents of its children. And let's do this with green. So this looks like this. And like this. And I'll say something for this in a bit. So here's the red. So these are the action states. And then with more colors.
Wait, so you don't include those nodes in the blue that are parents of other nodes in blue?
I think not, no.
Uh-huh.
So, okay. All right.
There are more colors. Did you want colors?
Yeah. Sorry, I'm getting kicked out of the room. I'll need 3 minutes to come back. Sorry.
Sure, no problem. See you in a few minutes.
Yeah. Yeah, sorry.
Yeah, no sweat.
Yeah, you had some conversation about structured, like hierarchically structured.
Yeah, we were just Will was asking me why I was sort of grilling you a bit on whether hierarchy was somehow the first thing I need to think about when I think about agents. And I was sort of explaining why it's not always the case that the key is to subdivide and think about hierarchy. I mean, to give an example, it's sort of people have been going on and on since the beginning of deep learning about how important it would be to hard code hierarchy into deep learning systems, and that always turned out to not be the key to understanding anything. Maybe in the next generation it will be, but it's not like it's sort of obvious that hierarchy might be useful, but that doesn't mean that it's always the right thing to do, to think about things as being hierarchically structured.
Yeah, sure. So
but I'm not saying that in this case it's not useful or something. It's just in general, that's why I was asking.
Right. Yeah, I guess I just want to say something more about that. It's obviously if you want to create a system that works well, like in a system that is very capable in some say like a neural network or machine learning model, then that doesn't necessarily mean that you cut reality at its joints or something. So natural abstractions is also really about abstractions in the territory instead of in the map, right? It's why can we abstract at all? That's not a given. It's not clear that is even possible. There's another Einstein quote, I guess, which is something like, I already forgot it, but it's something like the most extraordinary thing about the world is that it is understandable at all. And part of that is that there are many systems that are sort of abstractable, meaning they can be compressed very fruitfully with a few number of high-level summaries. There are very natural ways in which these hierarchies also occur in this sense. All right, let me go on with the rest of the talk. So, so this is kind of the definition of what I drew. So it is a joint probability distribution over all these variables. So they're all called xi, and there is a specified factorization that you get from the graph, basically. So it means the joint probability distribution factorizes over the product of all the individual variables where you condition on their parents, right? Their parents causally determine their value. And this is Bayesian networks, and this is really the birth of causality theory, which is like still totally underutilized the answer to everything. Okay, so let me see. So a Markov blanket of a random variable in a set of random variables S is any subset S1 such that Y is independent of S conditional on S1, right? So if you know the values of S1, then kind of Y is completely shielded off from the rest of the world. So when we look at the picture, it's very clear. Okay, we have the blue. Right, it could also be a collection of variables. So instead of one variable Y, we have a couple of variables. And then we look at the sort of a collection of variables that shield off that from the rest of the world. Now, the thing I drew is not just a Markov blanket, it's a Markov boundary, meaning it is a minimal such Markov blanket. Right? We could enlarge it. It's still going to satisfy the independence axiom, but we want some sort of minimality.
Sorry, could you mark S and Y on that diagram for me? An S1.
S1. S.
I see. Mm-hmm.
Yeah. So where is the next? Does anybody know?
Yeah. Let's walk.
Okay, I didn't know there was more, so there's no orb cam, sorry.
That's okay.
You're gonna have to ask everyone to disconnect
Oh yeah. All right.
the orb.
Okay, so this world isn't quite finished, so apologies for that, but disconnect from the orb now, please, by clicking the listener button at the top of your screen, and the halo around your head will disappear. And when you've done that, this way, please.
Do I need to do that too? Or?
Yeah, you can disconnect as well. Yeah. Okay, you've done your exercise for today.
Right.
So there's no orb here, so maybe if you just stand in front of the board, we'll just click on it and read it as you talk about it.
Right.
Yeah, sorry, I had no idea there'd be more.
Oh, that's my fault. Yeah.
Yeah, so it means S1 contains at least all the information one needs to infer Y. The variables in S1 are redundant. A Markov boundary is a minimal Markov blanket, right? So it's a such that it's minimal. So little question, is the Markov boundary unique? And there is a subtlety here, and I won't go into that, but it's an interesting subtlety. It has to do with vectored sets, with this Scott Garabrandt's sort of a new idea about Scott Garabrandt. It's also related to how did I pick these variables in the first place, right? If I have a bacteria, we haven't even talked about abstraction, but before you do that, you pick which variables you measure somehow. And if you have two variables, x and y, then you can make a third variable, which is x XOR y. And so if that's C, then any two of these three will determine the other two. So this is also, maybe if you've heard about the lean group problem in philosophy, it's kind of related to that. So I sort of cheated a little bit. There's one step about examining a system, a complex system, that is non-trivial, is about picking the right variables in the first place, and the right causal structure in the first place. But okay, we're just going to assume that's given and that it's given in a good way, and then it's going to be usually unique. So for realistic situations, we probably want to really consider epsilon approximate Markov blankets and boundaries. So, right, so obviously all this will be, you'll have to like actually measure it using sampling, and there's some errors. Anyway, that's a little remark about like how you really, the kind of things that come in if you really want to do these kind of things. So the cell boundary is sort of the archetypical example of the Markov boundary in some approximate way, right? Obviously, it's not. Yeah, okay. I'm not going to say too much more about this, but it's a very good approximation. Now there's observation. Yep. Hello.
I think it wasn't a question.
An observation. There's an observation. I don't know. I've seen it in Tristan, but Tristan is I have big doubts with this guy. So he's kind of he doesn't overstate stuff. A lot of errors in his work as well. So but anyway, this is still kind of interesting idea, which is if I have a Markov, let's say, boundary, then it sort of decomposes. You have the internal states, which is the blue thing I started with. The external states, it's everything outside the Markov boundary. And the Markov boundary itself decomposes into states we call observation states and action states, right? Sort of the incoming things and the outgoing things. Now, this is easily overstated. It's not the case that if you just have a Markov boundary, then you suddenly have an agent with actions and observations. It is rather, if you have an agent, you have to, or if you try to find an agent, you're going to try to find the boundary of that agent, and then this is sort of a natural way of how it slots into action states and observation states. But just having a Markov boundaries was not enough to really talk in a meaningful sense about an agent. It's too little.
Intrigued by the observation state that is a parent of the action state, but not of anything that's in the internal state. What is the action states you're kind of suggesting are the children in the boundary of the internal states, which makes sense. And I guess I get that observation states would be things that are parents, that their children are all, well, at least some of them are internal states. I guess they shouldn't necessarily all be internal states. But what's this other one? How do I think about that? So this one here is
I'm gonna say that I don't know. I'm also a little confused. I find this confusing as well. It doesn't quite fit in the rest of the story.
It's an intriguing idea, though. I hadn't thought about this, but it does make sense. Yeah, interesting.
I don't know if you have an idea what this like little thing could be or something. I probably have to think about like confounders and see. Yeah, interesting question. I'm afraid I can't answer it. So, right. So maybe you can make like a simple observation that sometimes they actually sort of decompose into irreducible components. It can be more useful to think about the irreducible components. Right. And then, all right, more about Markov boundaries. So another aspect is that they can be nested. And so you have these nested Markov binaries or blankets binaries. And well, it's very natural if you think maybe about neural network, or you think about well, cell structures also have these nested boundaries. Anyway, very natural. And then, well, if we have a nested one, we can do a quotient. So if you click on it, I drew it. Hopefully it makes sort of sense, right? I have a boundary B1 and B2, and then I collapse B1. So I kind of, from this perspective, ignore all the internal structure. Yeah, probably some operatic Kabbalah going on.
Well, it's
very...
I'm glad you drew this picture, because making the link between this picture and renormalizing a lattice model is kind of we could draw the same picture, so it's a good start.
Yeah, right. I was kind of, yeah. I don't know enough about anything really about normalization, but this felt similar indeed.
You could say literally the same thing.
Hope
that you collapse it to a single node in a way that kind of still preserves your ability to understand the dynamics, which, I mean, in this case, the dynamics would be, I mean, you could set up a Boltzmann distribution whose evolution was governed by the factorization of the Bayesian network. And I mean, probably you could literally think about this procedure as being renormalization of an associated kind of theory. So yeah, that's very interesting.
Well, I think we should get you in contact with David Spivak to turn all this into invoke the Kabbalah. Yeah, this is his forte. All right, so yeah, so now we come to the third topic. So we have utility maximizing, we have sort of boundaries, and also maybe implicitly how to see these boundaries, Cartesian boundaries, and also kind of the limits of them. Anyway, that was topic 3, and the third is how do we infer agency? That's really the fundamental, a really deep question. Yeah, so all these 3 topics are sort of loosely related, but okay, so how do we infer agency? Well, what we want is we want to sort of first find out like a good collection of variables that make sense. And I already said something about the vectored sets and how do you actually find these causal structures. Very interesting question. Then you get something like a causal Bayesian network. But sometimes you have symmetries. There are a bunch of more, like, things that make it more complex, obviously. And then you want to sort of try to find the agents in there. And the first step is like finding these boundaries. An agent has a boundary, or an approximate boundary at least. And then the next step is the goal is to apply selection theorems that tell us when a system is optimizing for a certain goal or utility function. So we sort of, very degenerate form of the selection theorem is, or maybe it's not correct to call collection theorem, but the von Neumann axioms of rationality state that if you have certain preferences, then that's given by a utility function, certain conditions on your preferences. That doesn't tell us when a system has preferences in any sense. So preferences only make sense if you have options and you can choose from these options. So anyway, I won't say more on that right now, but that's where you want to go. But before we can feasibly do that, we need to understand abstraction better, right? We need to compress a lot of the huge amount of variables that occur in complex numerical systems like market societies, brain neural networks, a small set of key variables. So far I've been talking about agency as a form of abstraction, but abstraction is a little more broader, right? Not all abstraction is a form of agency, although I would say agency is sort of the queen of abstraction. All right, so Wentworth said abstraction is information at a distance. So that is one of its metrics. And all right, so this is a very simplified, so please don't make the mistake of thinking this is it, but for now, I think that makes a lot of sense. So we have some variables, and interactions between X and Y are mediated by noisy variable C. So noise in V wipes out most fine-grained information about X, so only the high-level summary is relevant to Y. So in other words, the probability of Y conditional on X is the probability of Y conditional on these summaries. Yeah, these Fs are the high-level summaries, which we'll kind of be very interested in. And one sort of instance of, well, the prototypical example of them are these sufficient statistics. So they are also Lagrange multipliers, show up as Lagrange multipliers of Max and distributions. So the distributions that you get by applying the max entropy principle, which is, some of you might know, but it's the basis of all static thermodynamics. So a typical one would be temperature, right? That's the Lagrange multiplier, the Lagrange conjugate variable of energy. And it is also one of these sufficient statistics. And there's another perspective on it, which is that sufficient statistics correspond to ergodic components of a dynamical system. Anyway, these things are all related. Get to the final slide. So I hope this kind of makes it a little more clear what I'm talking about. So we have the X, and we have the Y, and we have all these intermediate variables. And maybe in the future I'll say more about that, but Wentworth really makes a lot of the so-called telephone theorem. So maybe you've heard about the telephone game, where you sit in a circle and you say a word. And one person starts with a word, and you pass it through, right? And you whisper it through, and you've played it, then you know that if you have a large circle and that's adversary, then the word will be completely different when it gets back, right? So the noise wipes out a lot of the information, but not all of the information gets wiped out. If you only do single letter substitutions, those are the only possible errors. Then, for instance, the length of the word will not change. So there's some constraints that get preserved and some that sort of get wiped out by noise. And if there's enough noise, then you can sort of decompose it into these two bits. Right, and then these sort of deterministic constraints will be, or these constraints, they don't have to be deterministic. They're going to be these correspond to these high-level summaries. That was it, mostly. Yeah, so maybe I'll say one thing more about the, no, I guess I'm open for questions.
Yeah, it seems pretty clear the analogy to renormalization is appropriate. I'm sort of surprised it hasn't come up in a formal way in this literature already somehow. I mean, yeah, well.
I think John definitely knows about renormalization. I was thinking about this. There's also a story about like CA field approximation, which is more about finding these abstractions in the first place.
Yeah, I had a question about that.
Yeah.
Going back to the inferring agency slide, suppose that I choose my Markov blanket, or I decompose the low-level degrees of freedom in a certain way, which leads me to conclude that agency exists. But you decompose them in a different way, which causes you to conclude that there is no agency.
Yeah.
If that's possible, then isn't the notion of agency just kind of bunk? And it seems very hard to imagine you could prove that it isn't like that.
Yeah.
So doesn't this make it? I mean, it makes me pretty doubtful, I guess, that there is a well-defined notion of agency that could come out of this, even in principle.
Okay. Well, that's incorrect. that's keep the space. So the decomposing is really but related to vectored sets. So so this is really a broader issue than just the agency, but more about abstraction. Is I decompose a world in a certain set of variables, and you decompose it in a different set of variables. When we conclude very different things, especially when you talk about these abstractions and high-level summaries. So factored sets sort of gives an answer to what degree some decompositions are better than others, are the correct most elementary ones, the most primitive ones, and which ones are not that. So I would say that objection is going to get solved. There's another, so you mentioned some other sort of question about, is agency a real thing, right? Is it even, humans can reason about agency, but it seems kind of wishy-washy and kind of in the eye of the beholder. Why do we expect this has a mathematical, rigorous description? And I would say, we'll get there into that direction, but kind of re-emphasize that it is non-trivial that some systems can be abstractified. Some systems can, some cannot. And one of the really important theorems that we'll may hopefully see is the Hitman, Copman, Darboy theorem, which kind of describes the systems that can be usefully abstractified. Or anyway, it gives a very powerful answer to when are systems even abstractable. Not all systems are, or not well extractable. Anyway, it kind of gives an answer to that. So I really want to say abstractions are natural. They are not so much in the eye of the beholder as one might initially I don't know. If you're coming from a skeptical philosophical tradition, then you might think that doesn't mean that they're completely unique, right? Obviously, there are going to be some summaries, but they're highly canonical. And I guess the intuition is that agency is sort of one of the the queen of abstractions and very sophisticated abstraction, or kind of it needs all the tools from the tool shed, but it is a capsule motion. It should be mathematically understandable. We have many bits, but we don't have the whole story of that sense.
Very interesting. Other questions for Alexander?
Well, I either gave an incredibly clear lecture or incredibly obscure one.
No, I think it was the former. I guess, I'm looking forward to seeing, I think it was a great overview. I'm looking forward to seeing some of these assertions backed up. But yeah, it's certainly very interesting. Let me think if I have any more questions.
I guess I have a question. Could you maybe give a hint as to like where this is leading? I guess like what are you going to talk about in future lectures? What are kind of the big goals of this program?
Well, the goals are very big, right? Understanding agency, understanding natural abstractions. A very concrete goal will be this Hitman Darboy theorem, which is a kind of obscure theorem maybe, but it's very old, but it's very cool, which is about sufficient statistics. Sufficient statistics have been kind of a weird name, or I don't know, maybe technical sounding name, but they are very important. They different communities of scholars know them by different names. So they correspond with ergodic components in ergodicity theory. So every sort of good dynamical system can be decomposed into its ergodic components. These ergodic components sort of correspond with sufficient statistics. A sufficient statistic, and in thermodynamics, they also show up as these Lagrange multipliers. In complexity theory, they're called, complex system theory, they're called causal states. And I assume that these will also occur in this renormalization story, but I'm less familiar with that.
Yeah, maybe I'll pick up the answer at that point. Yeah, so there's Alexander's speaking about natural abstraction, which is one of 3 tracks in principle that we want to explore in tandem. And the other 2 are renormalization, which we've mentioned already today, which is, roughly speaking, a way of moving in the space of theories or space of Hamiltonians in such a way that you kind of zoom out on a physical system and retain the ability to, even though you've replaced you've coarse-grained or replaced more fine degrees of freedom with higher level degrees of freedom, still maintaining your ability to model the system. So that's a well-understood part of mathematical physics. And the third track is resolution, in the sense of algebraic geometry, resolution of singularities, which there are some well-understood connections between resolution and renormalization. You can think of renormalization of quantum field theories as literally being an attempt to divide by distributions, which is one thing you can do when you have a resolution of singularities. So in some sense, there's very close connections between those 2 topics, but in the context of statistical learning theory, they haven't been explored very much. So there's kind of thematic overlap, which is so profound that all 3 of these things have to sort of be talking about the same things in some sense. But I don't understand exactly in which way they're talking about the same things. So we're going to try and figure that out as we go along.
Cool. Yeah, thank you.
Yeah, you're welcome. Okay. Are there any further questions for Alexander? I don't know if he has time to hang around for a few more minutes, but there is something cool to come and look at. So if you're available for a few more minutes and want to have a look, please follow me. Oh, and thanks, Alexander. That was great. And thanks for being patient with the technical problems.
Are all like blocky at a distance.
Yeah, the low res version isn't so great. Touch the grass and you go back to the start.
Was this already here, this stuff, or did you put this in?
Ethan put all the rocks in. I drew the lines between them.
it night now? Did we walk that long?
Sorry?
Did we walk so long that it's night now?
Yeah, the time of day changes as you get closer to this object. This is some music that Will, my PhD student who was here earlier, made. How long have you been thinking about this kind of stuff, Alexander? Is this like a years old?
Sorry?
How long have you been thinking about this kind of thing? Agency, Markov, blankets, whatever.
Couple years maybe, but not like. Yeah, it's like 20, like only part of my time. Yeah, I'm mostly focused on logic, so.
Right.
Yeah.
So you're a big proponent, I gather, of the Do calculus.
Yeah. Oh, yeah. This is. Yeah. It's. I mean, causality in general. The Do calculus is one way to do it, which is very nice, but. The idea of causality is Pearl isn't the only person to come up with this thing, but yeah, so far it's been really underestimated, or underutilized, really, I think. And there are many notions, especially when you talk about sort of, well, for instance, if you think about agents, you want to know about like when does one system optimize another system to do a certain goal, and that is really an intrinsically causal notion. I don't know. And many of our complex ideas about, I don't know, something like responsibility. That's also causal notion. So Pearl, in his book, he tries to sort of ground a lot of legal concepts as well in terms of causality theory. So, yeah, I think we want to understand a lot of the concepts that humans use informally, but so far there's like no good formal theory. I think causality is often the really helpful ingredient of it. There's also a different strand that actually causality, causal reasoning is also essential in physics. There's this whole book, Causality in Physics, and then it gets into like retarded Green's functions. So it's like
sure, yeah. I guess.
Yeah.
So I guess I started reading Pearl's book and found it kind of curious. I don't have any use for it right now, it seems to me, but I guess I don't disagree that it seems important. If somebody gives you a Bayesian network, but I mean, what if I don't believe that there are Bayesian networks out there? I mean, can't you level at this point of view the same kind of issue that, I mean, all attempts to model the world using formal logic with variables crash on the same rocky shore, right? Which is that, in fact, the world is not made up of discrete elements satisfying relations, at least not in any useful way, once you go past the examples that fit in a textbook or that you can give to students at the beginning of a AI textbook. That's why we have deep learning. So I guess you can try and infer what the elements are, and I suppose that's part of what you're talking about today. How you can, but that's also a very old idea, which arguably hasn't worked that well. So if I'm not going to be able to model my system by a Bayesian network, if that's the first step, and then I think about it causally, I suppose I'm kind of nervous at the very beginning.
So do you agree that, would you accept that some systems can be usefully thought of as joint probability distributions?
Sorry?
Do you think that joint probability that systems can be thought useful, like real world systems? I don't know. You're like making neural networks or cells or something. You can usefully describe them using probability distributions.
Sure.
Right. I mean that's a very non-trivial story, right? Making the connection from sort of the physical world to probably what is it probably discrete? Well, it's a certain function on the sigma algebra of sample space. What is the sample space? And then you have these variables. I mean, where are they coming? There's a lot of things going on there. Now, what is a causal model? Well, the only thing is that it's a certain factorization on that joint probability distribution. Now there are multiple factorizations, and some of them are better than others. With just observational data, you cannot distinguish most of these factorizations. There are multiple causal models from how to what you observe. If you have interventional data, if you can intervene, then you can ask can I intervene completely, or maybe it's messy? A lot of interesting questions there. But then I can distinguish maybe way more, and then I might be able to find even a unique one. So this is sort of causal inference, you could say. But I don't. I think if you believe that probability theory can be used fruitfully in the real world, then I think it's a very small step. Thinking of the software.
Yeah, I think it's. Yeah. Well, I would think that small step is actually quite big, but maybe we can argue about that some other time. Yeah, I mean, I accept the point. I think that's fair. Cool. Thanks a lot, Alexander. I think that was a great start to the seminar. Thanks, everyone.
And there's alignment, there's safety stuff. Or what is that?
Actually, unfortunately, Matt had to.
I see. Okay.
Was otherwise occupied, so there's no AI safety seminar today.
All right.
Thanks, everyone, and see you next week.